Hello everyone, we continue with computer system architecture course and our topic is floating point operations. In the previous videos we discussed addition and subtraction, multiplication algorithms and division algorithms. All general purpose computers support floating point operations and almost all programming languages have a facility for specifying floating point numbers. The most common way is by the real declaration statement. Floating point operations are usually hardware implemented. This is more expensive than implementing them using software, but it's more efficient. One of the examples is the AM9512 processor that provides the operations add, subtract, multiply, and divide for 32 and 64-bit operands. A floating point number consists of two parts, the mantissa, M, and the exponent, E, and has the general form M multiplied by R to the power E, where R is the base or radix of the numbering system used. Usually R and the location of decimal points are assumed, and they are not included in the register. For example, the decimal number 25374 is represented with M equals 25374 and E equals 3, and is interpreted to the following floating point number. Here the assumed decimal point 25374 multiplied by 10 to the power 3. A floating point number is normalized if the most significant digit of the mantissa is not 0. For example, the number 0.025E3 is not normalized. In order to normalize it, we have to shift it to the left one position and decrement the exponent by 1. And the number 1.03E3 is not normalized as well, and in order to normalize it, we shift it to the right one position and increment the exponent by 1. Floating point representation increases the range of numbers that can be accommodated in a given register. And this is one main advantage for using floating point representation. Consider, for example, a computer with 48-bit words, 1 bit of them for the sign. The range of fixed point integer numbers will be from minus 2 to the power 47 minus 1 to plus 2 to the power 47 minus 1, which is about plus minus 10 to the power 14. If we use floating point representation with 36 bits for the mantissa and the 12 bits for the exponent, and assuming a fraction representation for the mantissa and taking into consideration the two sign bits, then the range of numbers will be from minus 1 minus 2 to the power minus 35 to plus this value multiplied by 2 to the power 2048 minus 1. Since the exponent of 11 bits, 2 to the power 11, 2048. This is a fraction of 35 ones. And here the largest number that can be accommodated is approximately 10 to the power 615. Arithmetic operations with floating point numbers are more complicated than with fixed point numbers, and their execution takes longer and requires more complex hardware. First, regarding the addition and subtraction. Addition or subtraction to numbers requires first an alignment of the radix point, since the exponent parts must be made equal before adding or subtracting the mantices. And the alignment is done by shifting one mantissa while its exponent is adjusted until it's equal to the other exponent. Consider, for example, the two numbers 2.5 multiplied by 10 to the power 2 and 136 multiplied by 10 to the power 3. If we choose this number with this exponent, it's equivalent to 0.25. We shift right and increment the exponent. Now the two numbers are under the same exponent, so we can perform the add operation. In this case, we'll have 6, 8, 3. When a mantis is stored left, and shifting to the left, we lose the most significant digits. And when we shift to the right, we may lose the significant digit. So in most computers, shifting to the right is used, since it reduces the accuracy only, and we do not lose the most significant digits as in shifting to the left. The usual procedure is to shift the mantissa with the smaller exponent to the right by a number of positions equal to the difference between the exponents. So the two mantises will be under the same exponent. When we add two normalized mantises, an overflow may occur, and it can be corrected by shifting the sum once to the right and increment the exponent by 1. On subtraction, we may have an underflow. For example, the difference is 0.032. In this case, to normalize the difference, we have to shift the mantissa to the left and decrement the exponent. Here, for example, 10 to the power 4, then after normalization, it will be 10 to the power 3. We may require doing that more than one time in order to have a non-zero digit in the most significant position. Here we have the hardware flowchart for addition and subtraction of floating point numbers. First, BR 0, then we are done and the result is in the accumulator. Here is the case. If BR is not 0 and the accumulator is 0, accumulator 0 and BR is not 0. Then we transfer BR to the accumulator, and if the operation is add, we are done, and if it is subtract, we have to complement the accumulator. If the two numbers are not zeros, we continue. Now if the exponents are not equal, The matrix having the smaller exponent is shifted to the right and its exponent is incremented. This process is repeated until the two exponents are equal. Next, we perform the operation. For example, on add, if the signs are the same, then we add the two matrices, and after that, we check if we need normalization. If E is 0, then we are done. If E is 1, in this case, we have to normalize the result. E is transferred to the A1 bit of the A register, and the exponent is incremented by 1. In this case, we have into overflow. If the signs are different, we perform the subtraction A minus B here by adding A to the 2's complement of B. If E is 0, then we have to take the 2's complement of A and complement the sign. If E is 1, we have to check A. If it is 0, then 0 is transferred to the accumulator, and if A is not 0, in this case, we have to normalize the result. If A1 is 0, we shift left A1 and decrement the exponent, and we repeat this process until A1 becomes 1. Do you see this case if the result of subtraction, for example, is like that? Then we have to loop here until we'll have here 0.31. And I think it's easy for you to follow the other conditions. Next, multiplication of floating point numbers. The multiplication algorithm can be subdivided into 4 parts. Check for zeros, add the exponents, multiply the matrices, normalize the product. So in multiplication, we multiply the matrices A and B, and we add the exponents. And in division, we divide the matrices and subtract the exponents. The exponent may be represented in sign magnitude representation, in sign 2's complement form, or rarely in sign 1's complement form. And there is another representation used in many computers and known as biased exponent. Here, the sign bit is removed to be a separate entity. The base is a positive number that's added to each exponent as the floating point number is formed. In this case, internally, all exponents are positive. Consider, for example, exponent that ranges from minus 50 to 49. The base 50 is added. In this case, the exponent register contains the number A plus 50, where E is the actual exponent. And the range of exponents will be from 00 to 99, and not from minus 50 to 49. For example, if the actual exponent is minus 20, then after adding 50 to it, the actual exponent will be 30. The advantage of using based representation is that it will be simpler to compare the relative magnitudes of the exponents. Regarding register configuration, in general, the same registers and adders used for fixed point arithmetic are used for processing the matrices. Each of the registers A, B, and Q are divided into 2 parts. one part for the mantissa and the other part for the exponent. The mantissas are presented in sign magnitude representation and the exponent in the base representation. AS, BS, and QS are the signs of the mantissas. The most significant bit in A is labeled A1, and you know it should be 1 for normalized mantissas. A parallel adder is used to add the mantissas and transfer the result to the accumulator and the carry to the flip-flop. A separate parallel adder is used for the exponents. The exponents are also connected to compare circuit or magnitude comparator that provides 3 outputs: equal, greater than, or less than. All numbers before and after the operations should be normalized. Here we have the hardware flowchart for multiplication of floating point numbers. Multiplicand is in BR register, multiplier in QR. We check if BR is 0, then the product is 0, and we are done. If BR is not 0, we check if QR is 0, again the product is 0, and again we are done. If both operands are not 0, the exponent of the multiplier is in Q and is transferred to the A. Next, we add the two exponents A and B in A. Since both exponents are based by the addition of a constant, the exponent sum will have double the base, and the correct based exponent is obtained by subtracting the base number from the sum. The mantissas are multiplied as we discussed in section 10.6, and we check A1. If it is 1, then we are done and we have a normalized result. And if A1 is 0, then we have to shift left AQ registers and decrement the exponent by 1. And here only one normalization is required. Regarding division, floating point division requires that the exponents be subtracted and the mantissas divided. The division algorithm can be divided into 5 parts. Check for zeros, initialize the registers and evaluate the sign, align the dividend, subtract the exponents, and divide the mantissas. In division, first the two operands are checked for zeros. If BR is 0, then we have error, divide by 0, and error message should be displayed in this case. If BR is not 0 and the accumulator is 0, then the quotient is 0 and we are done. Next, the sign of the quotient QS is obtained by exclusive OR the signs of AS and BS. The sign AS of the dividend is left unchanged, and it will be the sign of the remainder. The Q register is cleared, and the sequence counter is set to the number of bits in the quotient. The two fractions are subtracted here, A minus B, and the carry E determines their relative magnitudes. In both cases, A should be restored by adding B to it. If A is greater than or equal to B, in this case, we shift A to the right one position and increment the dividend exponent by 1. Next, we subtract the exponents. Since both exponents where biased, the subtraction gives the difference without the bias. So the bias should be added to the result transferred into Q. The magnitudes of the matrices are divided as in fixed point representation. After the operation, the floating point quotient is in QR and it is already normalized. The exponent of the remainder should be the same as the exponent of the dividend. The remainder can be converted to a normalized fraction by subtracting n-1 from the dividend exponent and by shifting left and decrement until the bit in A1 is equal to 1. I advise you to take an example and follow the hardware flowchart step by step. For today, that's all. Thank you.